Okay, everyone, welcome to lecture 20. Today we'll be talking about dynamic programming. The goal here is to review from last lecture what we talked about and also uh, look at some more examples. Dynamic programming is all about going through examples and building intuition by seeing enough examples where it starts clicking in your head of how this counts as dynamic programming and how this works overall, right? I don't have a good way of teaching you exactly how to write a dynamic program. I can just show you a bunch of examples and hopefully y'all will build the intuition as time goes on by working through the examples and working on homework. All right, so let's go and jump right into it. Let's start by reviewing the topic and reviewing the definition from last lecture. Dynamic programming is a technique for writing algorithms on optimization problems. For example, optimization might mean finding the shortest path in a graph, finding the longest increasing subsequence, finding the total number of paths possible, finding the minimum total wait time, right? Like if I want to get everyone in a restaurant to wait the least amount of time collectively, maybe finding the best outfit, for example, from your wardrobe, stuff like that. Now, you can solve a problem using dynamic programming when you identify its optimal substructure, which is just a fancy way of saying you can express a problem in terms of a recursive subproblem. If I can create an optimal solution given the answer to a smaller copy of the same problem, same type of problem, then I can define this recursively and therefore the optimal substructure exists. Finding the optimal substructure is kind of hard sometimes. There's not, again, there's not like an intuitive way to do it for every single problem. You kind of have to think real hard, and I'll use your experiences and skills from the past in order to figure it out. Dynamic programming doesn't always produce a solution that's more efficient than recursion. Dynamic programming is useful and it produces an efficient solution when there's an overlapping subproblem in the recursive solution. All right, so we'll look at some examples today that explain that. Let's go ahead and take a look. So let's just remember how we want to think about writing a dynamic program. We want to start by thinking about the recursive algorithm that might solve this problem, or like come up with at least some recursive subproblem, and then initialize a table of solutions, update your table from bottom up using the subproblem, return the correct value from your table, and that's it, right? Like those are the general steps, but again, these steps are rather challenging to put into practice. And so the only way for us to take a look is maybe look at some of the following examples. So let's try thinking about pick trees. If you remember from homework 1, pick trees was the following problem. You build homes out of wood and you need material from a nearby forest. However, you want to avoid deforestation, so you decide for each tree you cut down, you leave the neighbors, so the tree on the left and the tree on the right, you leave them alone. However, you still need as much wood as possible, so that's the thing you're trying to maximize here. That's the thing you're trying to find the optimal solution for, right? So you have to be careful about which trees you pick to cut down. Right pick trees, which takes in an array of n trees, where array of I represents how much wood you can harvest by cutting down tree I. It should return the max amount of wood you can harvest while following the rules that we described above, right? So the question I have for you is, how do we actually solve this problem? Let's just try to solve this problem recursively. I'll give you all, before we do that, actually, let's look at some examples. Pick tree of the empty here. What should this return? What's the maximum amount of wood you can harvest if there's 0 trees? Right. Everyone typing in 0 in chat. That's intuitive. That's great. And what if we had an example like this? Take 10 seconds to yourself. Well, if we had these trees and we're trying to follow this rule, what should this one output next? Go ahead and punch in chat if you have it. Right, this should output 9 because we can go ahead and pick 1, pick 3, and pick 5, and that would produce an optimal solution here. I'll give you another 10 seconds. How about this one? Okay, everyone's typing in 6 in chat because we want to pick the 2 elements here. This one and this one. Now, for this example in particular, let's just imagine for a second we used a greedy algorithm. What would a greedy algorithm look like in this case for pick trees? So that's a question I want you to think about. What would a greedy algorithm look like for this case? I'll give you 15 seconds to think about it. What would you pick? What would be the picks that we would have if we went greedy for this example? Everyone said that the right answer is to pick the 2 3s, which gives us 6 overall. But in this case, another 10 seconds, what do you think the greedy approach would be? Give me an answer if you have it. Give me a question mark if you're not sure. All right, so in this case, when I say greedy, I mean like we can pick, for example, the one that'll give us the most. We'll get the most wood from picking this tree individually, right? We pick 4 first, and if we pick 4, then what's the next tree we can pick? If we can pick 4, then the next tree we're forced to pick is 1, because that's the only other tree that we're able to pick to include the total, right? So if we greedily picked the one with the most wood from a single tree, then the amount total would be less than the amount that we should actually get, which is 6, right? We would get 5 if we had 1 plus 4, because we picked 4 as the biggest tree. However, if we pick 2 slightly smaller trees, we would get more wood overall, right? So the greedy algorithm in this case wouldn't work. Pick the tree that harvests the most amount of wood, then pick the second most woody tree, etc. Right? Notice this isn't optimal. This doesn't produce an optimal solution. Right? So that's something to keep in mind. And if we just do one last one, we notice here we would pick this 5, skip the 1, skip the 4, pick the 9, get a 14 total. All right. Okay, so let's go ahead and take a look at how we would solve this problem. This is the original solution from homework 1. We would go and do this recursively, and I'm just going to walk through it step at a time because I know a lot of people got confused here and found this pretty challenging, right? We're going to go ahead and look at this example. So where we have the list 5, 1, 4, 9. And we'll bring it into our next slide here so that we can figure it out together. All right. So pick trees. Essentially, the solution I expected you to do in homework 1 was to try literally every single possible combination. Right? Try every single possible combination of tree picking, which meant that at each stage you're either picking the current tree or you're not. And we can go and express that by looking at this example here. All right, so we're going to look at this together. We're going to try to take a look one at a time in terms of recursive calls. Let's just start by calling pick tree of 5, 1, 4, 9. We know we can either pick it or not pick it. What I mean when I say we can pick it is that we'll end up with a result on the left-hand side when we decide to pick the 5 of 5 plus pick trees of 4 and 9. All right. We know that we can, if we pick 5, we can't pick 1. That means we're forced to only look at 4 and 9 left. So the code here does something very similar. It goes ahead and checks to see if we have an index that exceeds the list that we're at, which is the same as basically checking to see if the remaining list is empty, right? So this is essentially saying here, check to see if the list is empty, just like we saw in the previous slide. If the array is empty, then return 0. That's functionally what this is doing, right? We use an index instead because we can't actually make the array smaller by each step because that's a little bit hard to do in Java because arrays, you would have to make a new array each time if we wanted to shrink the size of the array. So instead, we just keep an index and we increment the index. And the first thing we'll do is we'll try to pick the 5. So we say array at the current index, which index starts at 0, so we get the 5, plus pick trees of array of index plus 2. So give me everything besides the first 2 elements of the array, and that will be my remaining list. Give me a smile in chat if you're with me so far, if this makes sense. All right, folks are feeling pretty good. Give me a question mark if you're confused, right? So again, this is checking to see if the index is greater than or equal to the array length because we're making the index go bigger. We're going to start actually from the left and go to the right, right? So this actually shouldn't be less than or equal to for that person who asked in chat. It's a good question. Hopefully it'll make more sense in a second. But if we don't pick the 5, then we could consider every other tree besides the 5, right? Because we didn't cut down 5. That means we can consider its neighbor. Okay, then that recursive call will look like this. Pick trees of 1, 4, and 9. Right? So this is the second recursive call we make. We make a recursive call here for pick trees of array and index plus 1. All right. And at some point, this will return some results and we'll take the max of the two. Right? So the recursive subproblem here, I'm just trying to explain how this works, and then we'll walk through the example one step at a time. So focus in with me on the actual code. What this is doing, these 3 lines, is that we compare the 2 values we'd get from the following, right? Cutting down the first tree and seeing how much wood we can harvest from there, right? Or cutting down or not cutting down the first tree and seeing how much wood we can harvest from the rest. Take the max of those 2 values. All right. So again, we're like simulating multiple universes. This is almost like just trying out every possible combination. Here, the first line here says, I will cut down the current tree, get the wood from that current tree, and then I'll make a recursive call to get all the wood I would harvest from the remaining trees I'm allowed to look at. In other words, in this case, I cut down 5 and I look at 4 and 9 as the remaining trees. I call pick trees, which will hopefully give me the right answer. Otherwise, I try not to cut down the 5, which means I can look at everything besides the 5, and those are the valid trees I can still cut down. All right. The max of those 2 values, the max of one of those values will give me the right answer. Okay. So in this case, this pick trees of 4 and 9 now will consider the new first tree that I want to cut down, right? The index now is pointing to the 4, which means we either cut down the 4 or don't cut down the 4. So what would be the code that, what would be the call that we would make if we cut down the 4? What would the left-hand side look like here? Go ahead and type in chat if we have it. I'll give you 10 seconds actually to think this through. What am I asking for here when we say pick trees of 4 and 9? What are the 2 recursive calls that get made? What are the versions of cut and don't cut that we have here? Go ahead and type in chat if you're sure. Give me a question mark if you're confused. Okay, everyone is confused. Great. So if we call pick trees, what I'm asking you right now is literally just focus in on this thing. Focus on pick trees of 4 and 9. All right. Give me a yes in chat if you're with me. We just focus in on this so far. All right. What that means is that we're going to go ahead and say pick trees of array and index, in this case, of 2, which is why we have 4 and 9 here, because we start at index 2 and onward. And we say, give me the tree at the current index, which is 4. And we're going to add that to pick trees of array and index plus 2 more. So we would actually have index of 4, which essentially means that we're calling pick trees on the empty tree here. Right? Functionally, that's what we're doing. Conceptually, what I want you to think about is I either use the current tree, in which case I add its wood value to the recursive call that I would make, or I decide not to use the current tree, in which case I call pick trees on the remaining trees left to consider. Okay, so what I'm asking you here is to think about how this would all work as we go on. So we called pick trees at this point of 4 and the empty list. What will pick trees of the empty list return? In other words, how do we hit our base case? What's going to output here? This is going to output 0, right? Just like we saw before. Even if you're not sure exactly how this code works, you should be able to follow along conceptually here. I'm not asking you to understand this code perfectly right this second. What I'm asking you to do is to think about a way to make the problem smaller. Each time we're making the array smaller by some amount. In actual code, we're increasing the index, which the index here is just the part of the array that we start on. At the beginning, we start at index equals to 0, which is why we have we start from 5, 1, 4, 9. We take the entire array. Then when we increase the index by 2, for example, we go 0, 1, 2, and we just have the array. We're considering the subarray starting at 4 all the way to 9, right? And when we increase the index by 2 again, then we're essentially saying the index is equal to 4, in which case we have effectively an empty array, which is the same as checking to see if the index has went over the total amount of array that we have, right? If index is equal to 4 by the time we get down here, and the original array has a length of 4, then this should hit the base case and return 0. Give me a base in chat if you understand how this base case, the checking of the empty, is the same as this code here, right? So if we have an index that just tracks how we're moving through the array, right? It says, okay, at the beginning, we'll start and consider the entire array. Then we'll move the index to be equal to 2, which means we'll start and consider only the array starting from index 2 onward, which is 4 and 9. Then we move the array up by 2 more, which means that we actually run out of elements to look at. So functionally, we have an empty array. But in reality, what we're doing is we're just checking to see what the index is, which in this case would be 4, and seeing that it's equal to the array length, which is also 4, which means we return 0. Right, so these two are functionally equivalent. Checking to see if the array is empty is what we're effectively doing here. All right, so at this point, we're going to go ahead and call pick tree on the list with just 9 in it. I'm going to give you all 30 seconds to make sure y'all are following. What are the 2 branches that we'll make here? Now that we've seen this pattern a couple of times, hopefully y'all are following along. What are the 2 calls we can make here in order to understand what's going on? Okay, go ahead and punch in chat if you have it. Question mark if you're still a little bit confused, right? If we look at pick trees with just 9 in it, we either pick the 9 or we don't pick the 9. If we pick the 9, we can include the 9 here, plus pick trees of the index moving up by 2. In other words, we just have the empty list here, right? The index here would actually be something like 5 once we go to the left-hand side, which would still hit the base case. And then here, we would call pick trees on the empty list. In other words, the index would be equal to 4, right? I've been offering extra credit every single section. The question I asked the last section was the first person who would tell me how to pick trees the way we've written it here gives me 2 to the n runtime. Would get 1 point of their final grade. So this is like a big boost to their final grade if they could explain it to my personal satisfaction. So this person earned 1 point of final grade extra credit, which is like a huge boost. Basically, if they had a, for example, if they had a 91 in the class or 78 in the class, they would now have 1 more. They would have a 79 or a 92 in the class. And I'm going to do the same thing here. If someone can explain in detail how this index actually is the equivalent of making the list smaller, the first person who explains this to my personal satisfaction will get 1 point bonus on their extra credit. And you don't have to do it right now, but I mean, some of you might actually go and start typing. I don't know. Some people made some memes here. I don't know why. But I guess if you want to make a meme joke, you can too. You just won't get the credit. But, you know, take time to do it thoroughly, because I'm not only going to give you the credit to the first person who makes me really happy that the post exists, like explains it very thoroughly. Because I know some people are still confused about how this indexing works. So the first person who can accurately explain why this indexing is the same as making the array smaller in this example will be good. There's the first post for each section. There's a different challenge for each section. So you have a different challenge in the previous section. The next section will have a different challenge as well. All right. Again, you can do it in lecture if you really want, but you're going to miss the rest of this stuff. If you feel like if you feel desperate enough to do this in the middle of lecture, chances are you're better served by paying attention to lecture and making sure you understand dynamic programming. I would try to type it up maybe after lecture, right? The question is, I'll write it in red here. Why does index in our pick tree, why is index in our pick tree the same as making the array smaller, right? So I said that in this case, the array gets smaller from this call to this call, right? I made the array go from 5149 to just 49. And what I did in reality was I increased the index by 2. And so how are those two things the equivalent here, right? So this is the challenge for the extra credit. We're on Piazza. Would we have to answer that? You would make a new post on Piazza, right? So you would make a new post here, just like how they did here. They made a new post explaining why this pick trees function is actually going to be O of 2 to the n. And they did a really thorough job. So this is the standard of work I would expect if you want to get the extra credit, right? So it's not necessarily easy to do this, right? And explaining it will help the class a lot. So this is basically going to go into your altruism grade for effort participation in altruism. Anyways, if we keep going, we know pick trees of the empty list will always return 0. So at this point, we're going to go ahead and output. Let's just make sure we understand what's going on here. This will, pick trees here will output 0. Pick trees here will output 0, which means at this point, we'll have a 9 on this branch and a 0 at this branch, right? Now, we just take the max of these two values. So that means pick tree here will output 9. If we keep going, what should come out of this line? What two numbers are we comparing at this level? If we do pick trees of 4 and 9, what are the two numbers we're comparing? Go ahead and type in chat if you have it. If we do pick trees of 4 and 9 here, we're literally just finding the amount of wood we can harvest if we pick the 4 and if we didn't pick the 4. So we're comparing 4 and 9 together. That means this thing will take the max of those two. So that'll give me 9, which means that if we have these two added together, right? Because pick trees of 4 and 9 gave me 9, will give me 14 on this side. All right. So if you're following along, hopefully this is not too scary. But the idea from here is that we're going to go ahead now and look at the right-hand side, right? We're going to do a very similar process where we look at all of the elements here. Which tree am I going to cut or not cut on this level? Go ahead and type in chat if you have it. Now that we're done with the left-hand side, we make the call to the don't cut version, right? So we didn't cut the 5, and now we have pick trees of 1, 4, and 9. What do we cut and don't cut here? Go ahead and punch in chat if you're with me, question mark if you're not sure. Right, so we want to cut 1 on the left-hand side. So we'll call 1 plus pick trees of just 9 in a list, in an array here, right? So if we don't cut, then we would just consider the world where we call pick trees of 4 and 9 on the right-hand side, right? If we call pick trees of 9 here, we've already done this process, so I'm not going to copy it. We know that this will output 9. I'm not going to repeat all the work. We know that this is going to be expensive because we repeat the same recursive calls over again, but we know eventually if we did this process again that this would output 9, which means if we add up 1 and 9, we would get 10 on this side. And we know from making this call from before that this will output 9. So instead of doing it all over again, I'm just going to go ahead and output 9 here. Which means that if we compare the 10 and the 9 together, we're going to get 10 on this side, right? Because we take the max of these two worlds. We either cut the 1 or we don't cut the 1. If we cut the 1, it turns out we end up with a slightly more wood. So we compare now 14 and 10. Obviously, 14 is going to be the biggest of the two. So we max out and get 14 here. All right. So the example here illustrates how we're going to use two different recursive calls in our function, in our helper function here, to either cut down the current tree and add the value of the tree that I cut down to the recursive call, or we choose not to cut down the current tree, in which case we just move on to the neighbor and consider everything from the neighbor onward, right? So we compare two different worlds. We either cut down the first tree and see how much wood we can harvest from there, or we don't cut down the first tree and see how much wood we can harvest from the rest, not the test. There's an R here, right? So we either say, okay, cut down the first tree, in which case we have to skip the neighbor and only consider 4 onward, or don't cut down the first tree and we can consider the neighbor onward. And we do that at each recursive call, which means that we try out every single possible combination of tree picking. We pick 5 here, and then we pick 4. We pick 5 here, we skip the 4, we pick the 9. We skip the 5 here, we pick the 1. We skip the 5 here, we pick the 4 here. Sorry, we skip the 1 here, we skip the 4 here, we pick the 9, right? I didn't draw out this tree, but you can imagine the rest here, right? And again, there is a world where we can actually make these recursive calls less repetitive, which is another way to make this effective. But now, instead of doing that, we're going to go and focus in on what the dynamic programming version of this problem is, right? So the important part to realize is that we have now our recursive subproblem. We either compare the first 2 values, we compare 2 values. We either cut down the first tree or we don't cut down the first tree. All right, that's our recursive subproblem. Remember when we're talking about dynamic programming, we have to look at the recursive subproblem, build out a table, and then from there, try out how we want to update the table and then return the correct value, right? So we're going to go ahead and use this idea to actually write some code now. All right, let me go ahead and pull up the replit. All right, so here's our pick trees from before. This is the recursive version, just like before. I run this, I get the correct answers for all of these. We expect a 0 out of the first one, 9 because we pick 1, 3, 5 here. We would pick the 2 3s for this one here, so 3 and 3. We would pick 14 because we would pick 5 and 9. And now we have some more complicated examples here, right? So this was our recursive version. I'm going to go ahead and hide it. What's more important is that we're going to write a dynamic programming version of this to try to understand what's going on. Okay, so at the very beginning, let's just go ahead and do some sanity checks. I'm going to start and code this and talk through it. And what I want you to do is follow along. At the end of the day, we're going to end up coming up with the correct answer, and I'll do a little bit more explaining at that point. But for now, let's just check if the array's length is equal to 0. If it is, then just return 0. This will make the rest of my code read a little bit more clean. So we want this here, right? Now, remember, the things we cared about, we initialize the table of solutions to the subproblem. In this case, I'm going to make every single element in my array its own subproblem. In other words, let's say that the subproblem here is going to be equal to how much wood could we cut down if we ended at tree I. So let's say that our max value of I is going to be equal to how much wood we could cut down if we ended at tree I. All right, does that make sense? Actually, I shouldn't ask that. And there's 50 of you. Some of you are probably confused. Some of you are following along. But let's just imagine for a second we had this array, right? So I'm going to call max values is equal to an array with some elements in it. And there's going to be a element for each index. So let's just imagine we had the first example here, right? So we would have 5 elements here. Cool. So how much wood could we cut down if we ended at tree 1? What do you think? What should the value of that be? Go ahead and punch it in chat if you're following along, right? If we say max value of I is how much wood we could cut down if we ended up at tree I, then we should get a 1 out, right? Because the first index, the only thing we can do is cut down the first tree. And so we would want to have that as our answer. Now, for the second element, by default, we could say that the best we could cut down is 2, right? Because that's the tree we can cut down right now. Or maybe there's some tree before me that we could have cut down that would give us more wood. We wouldn't know, right? So we would have to compare all of the values we had before me to see if there are any there that we care about, plus comparing to just what happens if we just cut down the tree right now, right? So in this case, if we just cut down the tree right now, we would get 2 here. And so our max value starting at 1 is 1, starting at 2 is 2. Everyone with me so far? Give me a smiley face in chat if you see where the 1 and 2 comes from. Give me a question mark if you're unsure. Right, big idea here is that we're setting the max value of I is how much wood we could cut down if we ended at tree I. Now, this third value, index 2 here, is going to be a little bit more tricky, right? We know that we could get 3 here on its own. That's a value we could possibly have. We could have 3 here. However, there's a better value, right? We could compare this 3. We can't add it to 2, but we could add it to 1. Right? Everyone see that we could cut down 1, skip 2, and then cut down 3 as well, right? So we would cut down this tree, skip the second this tree, and then get this tree here. So then what should this value actually be here if we were computing it manually? Yeah, we would get the 1 plus 3 and we could get 4, right? So there's this idea that we have to look back and see if there are some values that we care about that we want to consider, right? And if we do this one more time, we go and look at, in this case, this element here. How much wood could we cut down at this point if we're at this, like we could cut down just this tree here and get 4, right? But we could do better than that. We could, for example, cut down the first tree and then cut down the this tree here and get 5, right? So we could strictly do better if we cut down the first tree, skip, and then cut down this tree, right? Or what's some better option, even better option? Go ahead and type in chat. Which index do we want to cut down? We want to cut down this tree here. We cut down the 2, skip here, and then cut down the 4, right? So we're looking backwards each time. We get 6 here, right? And then lastly, we consider this here, right? Remember, when we were looking, let me just make this clear. Why couldn't we get 7 here? Why couldn't this be 7 instead of 6? I'll give you 15 seconds to think about it. Why couldn't we get 7 here instead? Go ahead and punch in chat if you're sure. We can't cut down neighbors, right? So there's this implicit idea that we'll look behind me. We'll look behind me each time, but we can't look behind me too far. We can't cut down the immediate previous neighbors. So we can't take this 4, for example, and add it to the 4 that we would have here and get some big value, right? Okay, so then let's look at 5. We know that at the last index here, we have this 5. So by default, we could start at 5. 5 is the best we could do. But we could also say that there's better, we can have a better value here, right? We could say that we can consider the 5 plus some previous value here. Now, of all of these values, we want the one that has the most value here, right? We can't pick the 6 here, but we could definitely pick the 4, which is why we would get a 9 here. And then we would be good, right? So that's what max values would be for this first argument here, right? Would this all increase? I mean, sometimes, not necessarily all the time. But let's go ahead and take a look at another example. So this was what happened when we solved here. But what about this one on line 8 here? Line 8 is a little bit different. So at the beginning here, let's just imagine. All right. What is the best value we could have at the very first element for max values? Go ahead and punch in chat if you have it. Right, we should have 5, right? Because we just used the 5. We have no other options. We use the 5. Cool. Then we go on. We see this 1. We can either cut down the 1, and we would just get a 1 here, which isn't very good, right? Or we can look at the previous element that we could cut down, right? If we choose not to cut down the 5, we could just pick the, if we choose not to cut down the 1, we could just pick the 5 from here, right? So does everyone see why this could be 5 here? Give me a yes in chat if you agree that index 1 for max value should be 5, because instead of just cutting down the first, the tree at index 1, we can just pick the 5 here, right? Okay, if we keep going here, then we can either say at this point, for is going to be equal. Okay, so can I say this again? Basically, I'm saying at index 1, I can either cut down the current tree, which gives me an exact wood of 1, right? Because I can only harvest this wood and I can't harvest any of the previous wood because there's only one neighbor to my left, so there's nothing else to consider. Which means that the most I could get here would be 1 if I just stuck with that. Or I can just say, okay, I don't cut down my current tree, right? As the rule here says, at each stage, I can either cut down my current tree or not cut down my current tree, in which case I can look backwards and say, hey, why don't we just cut down, why don't we just rely on the value of my previous neighbor? That was a better value than what I had now. So let's just pick that. Okay, so if we keep going, we're taking the current tree's value and comparing it to the values in max value instead of the original array. Yes. And I'll formalize this in a second. We're going to keep going here. If we pick the 4, if we decide to choose 4 here, we could either compare and say, okay, the best value we had previously is either going to be 5, right? If we don't cut down the current tree, if we don't cut down the 4, we could just get this 5 by cutting down by ignoring the 1 here and then picking the 5. That was the best value you could have be right here. Or we could cut down the 4 and we can add that to any of the distant neighbors, not the immediate neighbor here. So we don't consider this, but we can consider this 5 here and we would get 9. Right? So this 9 comes from the fact that we have 4 plus one of the previous neighbors that wasn't our immediate predecessor. Right? Type in 9 in chat if you see where it came from. Give me a question mark if you're a little bit unsure. Right? Again, we're just doing this approach. Conceptually, what we're doing is max value of I is going to be equal to the max of two things. We can either say it's the max value of I minus 1, or it's the max value, it's array of I plus the max value, the best max value from 0 to I minus 2. Right? One of the max values previously is going to give me a good value. Besides, this says go up until my exact neighbor before. I minus 1 would be my exact neighbor. I either used my previous neighbor's max value, or I look at everyone besides my previous neighbor. One of those will have a really good max value. I add it to my array of I, right? My current tree that I cut down, and I compare those two versions, right? This is literally what I have down here. Let me just actually arrange it so that the ordering is correct. So I either cut down the first tree and see how much wood we could harvest here, which is what I have here, or I don't cut down the first tree and see how much wood I can make, right? We're going and looking backwards. We want to look backwards because we're saying max value of I is how much wood we could cut down if we ended at tree I. So we're considering all of the trees up until now, and we're not looking into the future. So again, if we keep going and we look at this last tree here, now at this point, we're going to go ahead and say, okay, we have this 9. What is 9 plus the best max value from 0 to I minus 1? In this case, I is going to be index 3, right? I is equal to 3 when we're considering this 9 here. What is max value of I minus 1 here in this case? I'll give you all 15 seconds. If you're following along, I just want you to follow along one step at a time. What we're doing is we're trying to figure out the max value at I is equal to 3, which means that we have to figure out the max value of I is equal to 2. What do we get here? What is type in chat, what is the value at this point? Right, at this point, we should get 9 because max values of index 2 should give me a 9. And then we find the best max value of everything before me. Besides the 9 itself, from right here, we can pick one of the 5s from before, right? One of the 5s from before we pick just, let's say, this 5. And we will get, at this point, 9 plus 5, which gets us 14. Right, so the 14 shows up here. This computation should look very familiar. We're comparing two values here, 14 and 9. Of these two values, 14 is obviously the best, so we put 14 here, and then we're done. All right. So y'all see that we created this thing called max values, and we're going to update it as time goes on. Let's go ahead and write the code for it now. And let's see if this actually works the way we expect. So max values is going to be an integer array here of as many elements as there are elements in the original array. All right, give me a 32 in chat if you're with me so far. Let me actually fix this typo. New int. Right. As I told the previous section, I will sometimes make bugs. Please tell me when I make a bug while I'm typing. It's hard to lecture and code at the same time. It just takes a lot of mental overhead. So sometimes I'll like type in the wrong thing. All right. So this is max values. We're going to go ahead and we know at the very beginning, right? We know at the very beginning, max values is going to of 0 is going to be equal to just whatever the array of I is, array of 0 is. Because that's what we did every single time. Our very first element in max values is going to be just the current tree that I could cut down at index 0, right? Best value, most wood harvested at index 0 is just going to come from cutting down index, tree 0. All right. Oops. So the most wood we're going to be able to get from the very beginning is just going to be cutting down the first tree, because we're saying, again, max value is how much wood we cut down if we ended at tree I. From there, we're going to go and iterate for in I is equal to 1. I is less than array.length, I plus plus. And we just do exactly what we wrote here. Max value at the current I is going to be equal to math.max of two things. We can say that the first thing is going to be what happens if we cut down the current tree, right? If we cut down the current tree, we can get array of I, that's the value of the wood at the current tree, plus max value of I minus 2. Now you can see here that there's going to be a bug here, because if we do I minus 2 here, even if we have a 1 here, it's not going to work out. So we actually have to do a little bit of tweaking for our code. We have to check, for example, I'll show you this in a second. But for now, just imagine right now, max values of I minus 2, that's what happens. And then the second call that we have is going to be, okay, if we don't get the max value at I minus 2, we can just do the max value of I minus 1. And then at the end of the day, I can just return, instead of returning 0, I'm going to return max values of I minus array length minus 1. All right. So here's my code. All right. And I'll explain how this works in a second. Don't worry. It'll make a lot of sense in a second. We're going to look at it together. All right. Now, at this point, this doesn't work. This doesn't work because if we start at I is equal to 1 and we say I minus 2 here on line 37, what are we going to get? Give me the error that's going to happen if I have that, if I have this set up. Go ahead and type in chat or question mark if you're not sure. Right. Everyone notice that if I say I is equal to 1 and I say I minus 2 here, and we start at 1, then we have 1 minus 2, we get a minus 1 here. This would be array out of bounds, right? So we actually have to, when we're actually writing the code, add a few more edge case checks. So if the array length is equal to exactly 1, then we can say return the array at the current element, right? We need that so that we can do this code correctly and start at 2. All right. So then we set the max value of not only 0, but also the max value of 1 here to be the max, right? Math.max of either array of 0 or array of 1. Right. So the first two cases, I kind of have to hard code in here in order for this to work. Because at the very beginning, if I have an empty list, then none of this logic would work. So we would want to return 0. What? Why is this wrong? I think this should work. Otherwise, if there's exactly one element, then I'm just going to go ahead and return the element. Oh, yes, missing the else if. Thank you. Otherwise, here, if there's the length of exactly 1, then we can just return that element as well. Otherwise, we got to make a max value, which we said is how much wood we could cut down if we ended at tree I, and then set the max values of 0 and 1 accordingly, right? So 0 was always going to be just the tree at 0, and then 1 could be either the tree at 0 or the tree at 1, but they're mutually exclusive. For everything else, I can say, all right, give me the max value at I and set it to be equal to the max of either the previous best value we could have, like just considering cutting, looking at my neighbor, like my previous neighbor, its best value, or I cut down the current tree and look at the neighbor 2 before me and see if what their best value combined with my best value would be, and whatever the best of those two will be the value at myself. All right. Cool. So let's go ahead and just run this and see if this works. So instead of calling pick trees here every single time, let's call pick trees DP. I'm probably have some typos, so we're going to fix it. Oops. So we want the same numbers to repeat every time we use the dynamic programming version. We want the exact same answer, right? And this is our way of testing. And, in real life, I would do this too. If I had a slow version of a code and I want to write a faster version, I want to make sure the faster version actually gives me the correct answers, right? So if I compare the answers against the slower version, that's one way to do it. This is kind of janky, and in real life, you would test it more thoroughly and better. But we have like 2 minutes in the lecture, so that's what we're going to do. How did I copy the line quick? I have Vims as our key bindings, and there's a key shortcut in Vim that makes it really fast. All right, this error is max values instead of max value. Yeah, what I'm typing is Y, and then going to the right cursor point and then hitting P. So you can see here, we literally have the exact same duplicate answers every single time, right? This all feels good. So we know this works, but some of you might still be a little bit confused about how this works. So let's go ahead and work that out real quick, right? We're almost to a break. Just stick with me. I know this is really a lot of stuff to take in all at once, but let's just make sure we understand what's going on. The easiest way for me to explain to you what's going on is let's just print out the value of max value and just trace it for a single piece of code, all right? Actually, no, let's take the break first, and then we'll come back and do that. We'll take a 5-minute break at this point. And then we'll come back and explain what's going on, right? 5-minute break. We'll come back at, in this case, how does math work? 4:05? Yeah. Feel free to ask me any questions you have. Feel free to stare at this code. I also like this meme. Like, I'll show you this closer later on. Right, like, hey, everyone, he's trying to learn a new skill and still kind of awkward and feels silly because he's still learning. See, no one cares. Keep practicing, because getting good at something takes time. You're doing great, and I hope you become the master at whatever it is you're trying to learn. And that's basically the theme of algorithms, right? Like, no one cares that you're bad at it, or that maybe you can't code as well as you want to. That's totally fine. Everyone at the very beginning felt that exact same feeling of embarrassment that you're not as good as you want to be. The only thing you can do is, not worry about the fact that you're not as good yet, and continue practicing. Everyone is worried that they're behind. Literally everyone feels this way. So if everyone feels this way, then no one must be behind, right? By definition. So if you're feeling a little bit stressed by the fact that this code is hard for you, that's totally okay. We'll do our best to help you out. Yeah, if you're posting for extra credit, post it. You can tag either other or homework. Yeah, just tag other, I think, will be the most accurate. What if you're a little bit older? I mean, like, I think there are programmers who start late. I have a friend who's around your age who literally just started. And it took him a while to get going, right? Let me put it another way. He's in his 30s now. He started coding in like probably around 24, 25. So like he graduated college, or actually I think he dropped out of college for a while, came back in, switched his major from rhetoric to computer science, was the oldest guy in his class for by a mile, and I taught him in section. And then, like, now that he's in his 30s, he finally landed a really solid computer science job, like a very good one in San Francisco, making 6 figures doing what he wants. It took him a while to get there, but now he's a badass. And I would imagine that anyone else here can do exactly the same. Age isn't really, like, it doesn't matter, in my opinion, as long as you're willing to stick it through. And if you're, you know, in this class, for example, if you're trying to graduate with a computer science major, you're doing the right thing, you're headed in the right direction. A lot of it will just be practice and dedication and, you know, going through hard times for a while. There were some times with my friend where he felt very discouraged because he felt old and he felt like he wasn't getting it. And he saw all of these people that were younger than him getting really nice jobs. And it took him a little bit longer, but at the same time, you know, that's what he wanted to do. He decided to keep at it and he landed the job at the end. Question that's not related to the lecture, feel free to ask. How do I type so smoothly? Practice, I guess. I mean, I've been typing since I was a teenager and I have a nice keyboard, which helps. I don't know. What do you mean by typing smoothly? Do you mean fast or not making typos? Because all of that is just practicing and finding the speed at which you can still be relatively brisk and not make too many typos. Yeah, I guess it is an Overwatch themed keyboard. It's white and orange and a little bit of gray. But no, I for example, just go to like type practice. I think there's some this is one of the things you can do, right? This teaches you how to type faster. If you spend some time doing it, you'll get faster at it. And it helps you by identifying mistakes you make, and it tries to look at current, like, common patterns that people make mistakes on, and that helps, and it'll keep track of your progress over time, right? So that's like literally keybr.com. That's like one way to practice. All right, so we're coming back now from break. Let's go ahead and take a deep breath with me and type ready in chat if you're ready to follow along again. All right, so the thing I wanted to show you at this point is a raised.toString of max values, right? This is going to be a way to print out. Oops. Now that people called out how smooth my typing is, I'm going to make a million typos between now and the end of the semester. Just you watch, right? We're going to print out the max values and show you what it all looks like at the beginning all the way to the end for this example. This is a long example, right? So let's go ahead and just run this and see what happens. We know we're going to get 31 at the end, but at the very beginning, we start off with a bunch of zeros and 2 4s at the beginning, because what we're saying is the best tree, the most wood we can get from cutting down the current tree, right? Let me just make sure you focus in on the parts in red that we care about here. The best tree we can cut, the best amount of wood we can make at index 0 is just going to be cutting down the tree at index 0, which is where this first 4 comes from. The best tree you can get from index 1 is going to be either the tree you cut down at index 1, which gives us 2 right now, or we just cut down the tree at index 0, which is why we say math.max here, right? Type in 43 in chat if you understand the first line and you feel good about it. From there, we just follow this thing. Remember, this code is saying, or this slide is saying, come up with the recursive subproblem. So the recursive subproblem here is how much wood we could cut down if we ended at the current index. If we ended at tree I, how much wood could we cut down? It's either the tree that I cut down right now plus some best value from 0 to I minus 2, right? In other words, it's just a max value of I minus 2. Or max value of I minus 1, right? So this is almost like a recursive call because we're looking at the previous values of max value. We either say the best max value from 0 to I minus 2, which is just encapsulated by the I minus 2 here, right? Because this is cumulative, as some of you in chat have been saying. This only increases over time. So we only have to look 2 behind in order for us to keep track of what's the best value is, right? Yeah, so the shortcut I'm saying is that we go ahead and instead of saying the max value from 0 to I minus 2, we know that this is going to always be increasing. So all I have to do is type in max value of I minus 2 instead, because we know that the second to last max value that we have punched in is going to be the correct one, right? So in this case, we look here at index 2. So max value of 2 is going to be equal to cutting down the tree at 2 plus the max value of 0 here, because 2 minus 2 gives us 0. Or maybe it's the max value at index 1, right? Either I minus 1, right, by not cutting down the current tree, or cutting down the current tree and looking behind to see what other trees we could cut down previously, right? And we only have to look 2 behind at any point in time, which is why we get 7, because we say, okay, cut down the tree here and then go 2 before me. This is all the tree wood we can accumulate if we just skip the cutting down the previous neighbor and cut down all the neighbors before that. And then we would get 7 because 3 plus 4 here gives us the 7. And if we compare the 7 against the 4, clearly the 7 is going to win out, which is why we have a 7 here. Give me a 7 in chat if you're with me so far. Right? We could replace the best max value from 0 to I minus 2 because we said that max values is going to be cumulative. We know that from the, as we see in this array, as we print it out, all of the values are increasing, which means what it's stored every subsequent value keeps track of doing all of the wood harvesting from all the previous values. So we just have the best value at the next index every time. Okay. So now if we go on to the next one, I'll go a little bit faster now. Interrupt me with questions if you're confused. We look at this node. We look at 9 here, right? This tree here, we can cut down and we can get 9. Well, we could either get the best value from before, which is 7, or we can cut down the 9 and look at the best value from right before that, which was 4. So somehow we can get 4 here, right? We don't know if the 4 comes from cutting down this current tree, which it doesn't. It comes down from cutting tree 0. But at index 1, we have accumulated the max amount of wood we can get up to this point, right? When we end at tree I, we might not cut down tree I. We might have cut down previous trees, but this is the best value we could possibly get. So then the best value here is either 7 when we don't cut down the tree with 9 in it, or the 9 plus the 4, which gives us 13. 13 is obviously greater, right? So just to make this clear, we do max here of 13 versus 7. In other words, what happens if we don't cut down this current tree, which is where the 7 comes from, or what happens if we do cut down the current tree, which is 9, plus the max value we could get by not cutting down our previous neighbor, which was 4, right? You can see here that this 4 comes from the fact that we actually chose the first tree to cut down. We skipped the second tree. We skipped we cut down the 0th tree. We skipped the first tree. We skipped the second tree, and then we cut down the 3rd tree here. So somehow this 4 actually keeps track of that fact that we actually don't cut down the 2 here, but the 4 comes from the fact that we cut down a tree previously. Give me a 13 in chat if you're with me, if this feels good. All right, I'm going to move even faster now. Now, at this point, we're looking at this 4 here. And at this point, we can either say, okay, if we cut down the 4, what's the value we're going to get here? If we cut down the tree with 4 in it, what's the best value we could get, including cutting down the tree? Go ahead and type in chat if you're with me. What do you think this will get? If I cut down the 4, if I'm trying to figure out this value here, what's the value we would get at this point when we're at index 4? Go ahead and punch in chat if you have it. Okay, what I'm asking was the 4 plus the 7 here, right? The 4 plus the 7 gives me the 11, right? I wasn't asking for the total value. We know the total value is going to be 13. But we know that the best value we could get if we were forced to cut down the current tree is going to give me 11. Because we could cut down the current tree, we would have to skip our neighbor, so skip the 9, and then consider all of the values, the best combination of trees we could get down previously, which would give me 7, right? And we know that from cutting down 4 and 3. which is where the 7 comes from. So we compare, in this case, the 13, which is the best, 11, which is the best value we could get if we cut down the 4, against the 13, which is if we don't cut down the 4 and just pick the neighbor, right? The best value we could get from previously. It turns out the 13 wins, and this is where the new 13 comes from, right? We do this again. Okay, now we're saying, okay, is 13 good, or is cutting down the current tree, which is 5, and skipping the previous neighbor and getting this 13 good? And it gives us 18, so 18 is definitely better, right? So again, we're comparing 18, which comes down from cutting down the 5, right? Because now we're looking at, just to do this one more time, we're looking at the 5 right now. If we cut down the 5, we consider what is the best value we can make from all of here. Well, all of here comes and gives us 13. 13 is the best we can do by considering all the previous trees we could cut down along with the 5. And that gives us 18. We compare that to what happens if we don't cut down the 5, which gives us 13, right? Because that's the max value from the previous index 4. And we know that since 18 is better, we get 18 here. And then all of these get updated, right? 24 gets updated because comparing 11 plus this 13 gives me 24 versus the 18 that we would have if we didn't cut down the 11. So 24 is obviously better. If we have a tree here that's 0, well, 0 is not going to give me anything. So we're essentially at this level going to compare max of 0 plus the 20, the 24 from before and the 24 from not cutting it down. So it doesn't matter if we cut this down or not. We'll still get 24. Sorry, my bad. Let me fix that. This should be 18. Right? We're considering 0 next, which means that we can either look at 0 plus the 18 or the 24 from before. So we either, this tree isn't grown as a sapling, so we don't cut it down at all. It gives us 0 wood. Or we can just consider looking at all the other trees that we decide to cut down instead. If we skipped this tree, which gives us 24, right? So 24 beats out the 18, which is why we have 24 here. 30 comes from 6 plus 24 here. And then 31 comes from 7 plus this 24. All right, and ultimately we get 31. So if we just diagram all of the things we care about here, looking at this code, we know that we needed a recursive subproblem, which we have here. We needed a table of solutions, which is what this stuff is, max values here. And then we update the table from the bottom up, which is this code here. And at the end of the day, we just return the correct value from the table, which in this case is the very last element, right? So all of the 4 steps are expressed here. Number 1, which was finding the recursive subproblem, right? Number 1 was right here. Number 2, initializing our table. These 2 values had to be initialized here, right? Number 3, we had to update the table as time goes on. And you can see here that I've explicitly made this table. This is essentially our table here when we print out every single row. And then number 4, we print out the right answer from our table. And that's it. That's how a dynamic program works. Now, the runtime for this is going to be O of n, because you literally just go through and you update an array. And if there's n elements in the array, and if updating takes O of 1, then you have O of n total, where n is the number of elements in my array. So this pick trees is going to actually just give me this pick trees dp is in O of n, where n is equal to array.length, right? And as I alluded to before, the previous pick trees that we had up here, this thing here is actually going to be pick trees of is going to be n of O of n to 2 to the n, right? So this pick trees is really expensive. It's actually quite expensive here, right? It'll look something like this versus linear, which would look something like this, right? So this is really fast compared to what we had up here, and that's why we care so much. That the dynamic program that we just wrote is way faster than the recursive program we wrote in homework 1. Space complexity, we can actually simplify this. There's a version where it's even better, where we can simplify this space complexity to use constant space. Right now, we have to make a new array of size n, which means that we'll have a space complexity, which is O of n here. Here, O of n space complexity, because we have to have this max value, which we know is as big as our original array. But there's a better version which uses less space here and has the same runtime, which we'll look at later. All right. So the things you need to focus in on is being able to understand and explain this code, knowing that this code has O of n time complexity, O of n space complexity, and identifying the 4 parts of the dynamic program. In other words, number 1, which was the subproblem here. Number 2, which was initializing our table. Number 3, which was updating the table. And then number 4, which is returning the right value. In the for loop, why do we start at index is equal to 2? Because remember, we want to be able to look back at either my previous tree or the tree before me, and we've initialized the first 2 values. If we've initialized the first 2 values, then we can start from 2 onward. And we had to initialize the first 2 values because if you remember us manually solving the problem, we know that the first 2 values are kind of special cases because we can't look back and say max value of I minus 2. If we are at I is equal to 0 or I is equal to 1, right? We would get index out of bounds errors here and here. Does that answer your question? We have to start a little bit in our array, otherwise we'll get index out of bounds. Right? Okay. Now we've looked at dynamic programming. I'm not going to look and show you the better version. I'll code that up and I'll include it as part of what you need to learn. But let's go ahead and now focus in on this idea of greedy versus dynamic programming in the 10 minutes we have left. Both greedy and dynamic programming solve optimization problems. What I mean is that we have, for example, find the shortest path. That's an optimal optimization problem. We can have different paths from A to B, but there's one path that's going to be like the best path from A to B, right? Or if there are multiple paths that are the best path, they're all tied for first. Find the best outfit, finding the biggest profit, find the minimum waiting time for all customers cumulatively, right? In total. All of those are optimization problems from lectures around greedy programming and lectures on dynamic programming. In other words, you can use greedy programming and dynamic programming to solve the same set of problems, and they both require this idea of having an optimal substructure. So the types of problems they solve oftentimes can be solved using recursion. Now, we know that sometimes greedy programming is not going to work, right? Sometimes greedy programming can fail to produce an optimal solution. We know that because when we looked at our first lecture on greedy algorithms, we knew that make change 2, for example, when we use the greedy approach, it didn't work, right? And there's specific times when we want to use greedy. But it turns out that dynamic programming can solve and get the correct answer when greedy programming fails. However, it oftentimes costs us more time and space, right? It's often more expensive. So what I'm saying here is that there's a gradient of problems we want to solve for optimization problems. First, try greedy, because that's going to be oftentimes the cheapest. Then try dynamic programming. And if that doesn't work, then we have to try something like naive recursion or, exhaustive search. Try every single possible combination. And we want to try in this order because greedy programming is often kind of cheap. And then dynamic programming is a little bit more expensive. And then obviously exhaustive search is hella expensive. It's like 2 CN, right? So that's our order of operations in order to try out different programs. Now, the one way to see this, why greedy sometimes doesn't work and dynamic programming is better, is to revisit a problem we saw when we were considering graphs, right? Back when we were looking at Dijkstra's, there was this problem called single source shortest path, which took in a weighted graph with edge weights that are all positive, right? Remember when we did Dijkstra's and we picked the George and all of that, all of the edge weights were always positive. And the graph can be directed or undirected. That's fine. And the source node is where we started out at, and we would figure out what's the shortest path from S to every single other node that it could reach. And we could find the actual paths for it at the same time as well. right? But what if we broke that rule? What if we ran Dijkstra's on some negative edges here, right? Let's say we started with S is equal to A, and we're going to go ahead and run this, and we try to run Dijkstra's on a graph with negative edges. We know that Dijkstra's is going to be greedy. All right? So we know this will probably fail. All right? I'll give you all 30 seconds. What is going to be the optimal solution? What should distance look like if it were perfect? Distance, if it were perfect, what do we think it would look like? 30 seconds starting now. Right? I want you not to run Dijkstra's, but just to think, if we're going from A to every single other node, we know that A to itself is going to be 0. And then we have a bunch of other values we need for going to B, going to C, and then going to D. All right, what's the cost it will take to get to B? What's the cheapest cost to get to B? Go ahead and type in chat. In this graph, just visually inspecting it, we know we're going to have a 1 here, right? It's going to cost 1. Sorry, not 1. Wait, you are all wrong. I was wrong. You're all incorrect, right? Going from A to B is cheap, but even cheaper is going from A to D and then D to B. We all got baited, right? It's minus 201, right? We go from A to D, which adds 99, but then we go from D to B, which subtracts 300, which is super good. So we want that. All right. That means that going from A to C would be equally cheap. It should be minus 200 because we would go from A to D, D to B, which gives us minus 200 so far. And then we would just eat this cost from B to C, which gives us minus 200 overall, which is still super cheap, right? There's no cycles in this graph, so we don't have to worry about looping around. This is a directed graph, and it's acyclic, so it's a DAG. And then going from A to D is going to be expensive no matter what, because there's only one path to D, and it costs us 99. All right? Type in green in chat if you're with me so far. All right. So this is what we have for the correct answer. This is what we want. This is not what Dijkstra's is going to give us, but this is what we want. All right? So in this case, let's just go ahead and try to figure out what Dijkstra's is. I'll do it in reds because it's going to be terrible. It's going to be wrong. Distance starts with a bunch of infinities. I'm not going to update the prevs because we don't have the time. And at the very beginning, we set distance at S, which we're going to say is A here, to be equal to 0. All right. So far, we pick A, we set it to 0, and then we go ahead and do this stuff down here. We pick the cheapest node, the node that has the least cost going to it from A, and we process it first, in which case we pick A first. A is the first node that gets picked. We update all of its neighbors. In this case, going to B is now going to cost 1, right? So what we had distance of this before, now we have distance of this, right? This is what happens when we update B, and then we also update C, right? And then we update D as well. All right, this is what happens when George is A. In other words, we pick the first U coming out of the priority queue, and we get this. This is wrong. This is 99. All right. Give me, if you feel like you're following along so far, and this is what distance is right now, tell me which node do we examine next and what changes about distance. I'll give you 30 seconds. Which node do we examine next if you remember how Dijkstra's works? Remember, every node we pick out of the priority queue, it's the next cheapest node that we haven't visited yet, right? Remember George, that's how we go about it. Go ahead and type in chat, which node do we visit and what happens after we process all of its neighbors? All right, we pick C. Everyone's typing in C in chat because that's the next cheapest thing we haven't visited. And distance doesn't change at all, right? Because it has no neighbors to process. This is a directed graph, so C has no outward neighbors. We can't go to any neighbors from C, and therefore nothing updates, right? Cool. Then we visit the next cheapest thing, which is going to be B, right? We visit the next cheapest thing when we update the cost here. Well, B doesn't update anything either because the only thing it can get to is C, and C is already really cheap. It's 0. All right. And then finally, we look at D. We look at D here. D updates its neighbors, which means we'll look and change B from 1 to minus 201, right? This is where the 211 comes in. Because going from A to D is 99, but the edge cost from D to B is minus 300, which means the new cost from going to A to B, instead of being 1, could be negative 201, which is way better. So we should definitely pick it, right? At this point, are we done? Yes or no, chat? Does Dijkstra's say we're done here? Does Dijkstra say we're done? We're getting a lot of no's in chat. But we visited all the Georges. We've crowned all the Georges. We're done. There's no more Georges to visit. We literally looked at every single node. We're done. Right? So the answer here I'm asking is yes. And as you can see, that's a problem because we didn't update the cost to go to C. Right? The distance that we get coming out of Dijkstra's is not the distance that we want. Dijkstra's is greedy. This is probably going to fail somehow, and clearly it did. Right? So what happened here? Yes, someone mentioned Dijkstra's by definition shouldn't handle negative cycles or negative edges. Yes, that's correct. But let's say we wanted to use Dijkstra's to try to solve this problem. Remember, Dijkstra's will always give you a answer for a graph with negative edges, but it might not give you the right answer. In this case, that's what happens, right? So in this case, why was this so broken? Well, Dijkstra's is greedy. We never updated distance of C again after visiting D, right? After we visited D, which is what we did on this last call here, we never updated distance of C again, and therefore we could never update this here. We need to find a way to force, how did I get minus 201? Minus 201 comes from the fact that we went ahead and updated the cost to get to B by going through D. The cost to go from A to D is 99, and then we go and add that to the cost to go from D to B, which is minus 300. 99 minus 300 gives us minus 201. All right, so we need to find a way to force our algorithm to consider nodes again and again in order to make sure that changes from the previous iteration affect the nodes we visited in the past. We can't just do greedy anymore, right? So a dynamic program could solve for a graph that has negative edges in a way that Dijkstra's produces the wrong answer for. All right, that's the big idea. So this is the code that we'll look at called Bellman-Ford. Bellman actually was the guy who invented the term dynamic programming. He was one of the first researchers that kind of coined the term, and he's well known. Obviously, if you're a researcher in a Western country, everything gets named after you. So that's why Bellman has a bunch of things coined after him. But the idea here, if you look, is very similar to Dijkstra's. If we just compare this to Dijkstra's, you can see here that the first part is exactly the same. But the second part, instead of having a queue, we're just going to go ahead and do this updating bit. Let me just go ahead and make sure that we're comparing the right parts correctly. So the parts with the same color on left and right are exactly the same. So we have this for loop when we look at all of the edges here, right? Which this is the equivalent here. Let me just do a little bit of a correction. So this is all the same, and this is all the same. The difference here is that instead of looking at every single node exactly once and looking at every single edge exactly once, we're going to look at every single node and then look at every single edge, like every single possible edge, right? Which means that we're actually going to do the number of nodes times the number of edges amount of updates. That means we're forcing every single edge to update every single time we go through. Since we have a bunch more updates, the overall runtime is going to be something like this. And you can see here, there's a little bit of logic here that does the check for negative cycles, which we don't have the time to cover. The important thing to notice is that the runtime here on the right-hand side is going to be, remember from before, v plus e times log of v. That was the runtime for Dijkstra's, which is cheaper than saying b times e, which is more expensive. Now, I need you all to read this walkthrough for homework so that everyone feels good about this. It's literally 9 minutes. 4-minute video, 5-minute video. It goes through everything you need to know about Bellman-Ford because we don't have time right now. Let's do takeaways because we're already over time. Dynamic programming and greedy programming solve the same set of problems. However, greedy programming doesn't produce the correct solution for certain problems. It'll give an answer, but it won't necessarily be the best answer. Dynamic programming is helpful in those cases. And as a result, dynamic programming is more expensive from a runtime point of view, right? That's all we had for today. Thanks for sticking it out with me. I'll see you all next week. Homework is due tomorrow night. If you have any questions or concerns, now's the time to ask. Thanks, everyone. I'll catch you soon.
Hey, Professor, I
what's up?
have